All right, I could see the film. I understand Lorentz transforms. I have problems with the conclusion that simultaneity planes are reality. I was asking, how do I know what understand here means? And then Paul keeps asking me about what rapidity is. I started to launch into a fun fact about rapidity, but I realized I want to get a little deeper into this mental block of Paul's with the problem with simultaneity planes as a reality. Here's the fun fact that I was going to show about Lorentz transformations, that when you take a matrix that looks like this with 0 and phi, or this is curly phi or var phi, off the diagonal, which represents rapidity, and then you take the matrix exponent of that, which is like an infinite sum, you get something that looks like this: e to the negative, or e to the phi e to the phi plus e to the negative phi over 2. That is hyperbolic cosine of phi. And e to the phi minus e to the negative phi over 2. That is the hyperbolic sinh. And then this is also negative of the hyperbolic sinh. These are both negative sinh, and this is cosh again. Basically, it's as follows. I did just fix this part of this so that it has 0 and 0 here. But if you take the matrix exponent of this thing, now what does that technically mean as an algorithm? You're going to take e to the x is equal to x to the 0 over 0 factorial plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus, and then just continue on forever. So there's a good reason that these e to the power of things are coming up in here, because that is exactly what this thing is doing, except it's doing matrix multiplications for each of these. And this 1 and this 1 comes from this term here, because x to the 0 is the identity matrix. Moving on, whoops. This matrix is cosh var phi, or curly phi, negative sinh var phi, negative sinh var phi, and cosh var phi. And this, then we can put 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0. The Lorentz transformation is ct prime x prime equals ct t, and then you put these things in here: cosh phi, negative sinh phi, negative sinh phi, and cosh phi. And if you are aware that these things can be replaced with gamma, cosh phi is 1 over square root of 1 minus v over c quantity squared. Sinh phi is beta gamma, or v over c divided by square root of 1 minus v over c quantity squared. Negative sinh phi is, sorry, this is negative as well. Same thing, negative v over c times square root of 1 minus v over c quantity squared. And this 1 over square root, this is cosh phi again, which is 1 over square root of 1 minus v over c quantity squared. And then we can put in ct x and ct x, and you can verify that once you pull all that out, that you will end up with t prime equals gamma times t minus vx over c Yeah, we're going to be dividing by that c, so that c squared, that'll be c squared over on the right hand. And x prime, sorry, this should be an x prime equals gamma times x, or wait, gamma. This is gamma times x minus vt, and in that case, this c and this c cancels out. So the only difference here is that this is written in the other order, negative vt plus x over here. So we have the vt term plus x over here. So that should give you some kind of idea of what the rapidity is. It's an angle. It's just not an ordinary angle. It's a hyperbolic angle instead of a radian angle. So I just showed you the matrix exponential of this fairly simple 4x4 matrix, and it gave you the Lorentz transformation: cosh, sinh, cosh, negative sinh, cosh, sorry. You do the same thing with a theta and a negative theta. Notice this is positive phi and positive phi. But when you do the same thing with theta and a negative theta, then you get cosine, sine, negative sine, cosine. So there's a couple of differences here. This one keeps radiuses around the origin the same. So it works with r squared equals x squared plus y squared equals constant. And this works with, say, s squared equals c equals x squared minus c squared t squared equals constant, or tau squared equals ct squared minus x squared equals constant. So, so these rotation transformations conserve x squared and y squared, and but these conserve either x squared minus ct squared or ct squared minus x squared. And those are in different domains, of course, because the x squared minus c, so if you got a space-time diagram, the along those lines, x squared minus ct, whoops, x squared minus ct squared is 0, and here x squared minus ct squared equals 0. And then each of these lines and these lines are regions where the absolute value of x is greater than x squared minus ct squared equals a real constant greater than 0. And these lines, or these curves, and these curves are x squared minus c squared t squared is less than 0. So let's go back to Paul's comment with the conclusion that simultaneity planes are reality. And he has no problem that they are called perceived reality in SRT. He does not completely agree with SRT, but yet he can apply SRT. So at the moment, his affinity to the SRT is unimportant. Affinity may not be, but familiarity is. So he says when he's writing English, he needs to follow the English spelling rules. When he's communicating while using SRT, he needs to follow the SRT rules. I think that's accurate. But what I want to do is make sure that he's familiar with these laws of SRT. So in the rotation transformation up here, with this one, the rotation transformation, which preserves r squared, I'm not going to draw any asymptotes. What I'm going to do is draw circles. These are the regions that preserve x squared plus y squared. So here's the thing. When you do this rotation transformation, is there anybody in the world that thinks that that line is going to stay in the same place when you do a rotation transformation? Or is there anybody in the world that thinks that that line is going to stay in the same place when you do a rotation transformation? No, there's nobody that would think that rotating this diagram would keep those lines in the same place. Everybody can tell that this line is going to go around that way, and this line is going to go around that way. Same question here. Does anybody in the world think that that line, which is called a line of simultaneity, does anybody in the world think that upon applying a Lorentz transformation to that plane, that it would stay in the same place? And does anybody think that applying a Lorentz transformation to that line is going to allow it to stay in the same place? No, no. That line will move and stretch along that direction. So this event is moved here, this event is moved here, this event is moved here. And likewise, that's the relativity of simultaneity, ROS, and then this point will move here, this point will move here, this point will move here. So stay in the same line, it's going to rotate, stay in the same line, and that's called the relativity of position. Now, did I do that right? Do I understand? No. Honestly, I make mistakes. Obviously here I've made I've blundered. I have the relativity of simultaneity going this way on this one, and the relativity of simultaneity going that relativity of position going that way. That's not the way it works. How many people caught me in that mistake? Probably not many, because this idea is not particularly well taught in the schools. Okay, so, and I make mistakes too, and I feel like, yeah, okay, so let's fix that. We'll have 3 lines there. Of course, that blue line is not going to go that way. Let's put those little arrows in this way and this way and this way, and we'll draw that new line in. It's going to come over this way, and that event moves over here, that event moves over here, and that event moves over here. And that is the relativity of position. So honestly, I don't know if doing that had anything to do with understanding so much as memorization. I mean, really, at some point, a lot of human understanding doesn't come from reasoning, or a lot of intuition doesn't come from understanding, but from memorization. And so this is more what I would like Paul to go for, is kind of like not necessarily going back and wondering and doubting every time anything comes up, but just to have a good memorization of the phenomena under consideration. And I need to work on that too. I often complain that my memory is very poor, which is one of the reasons I make these videos. Okay, so I think I'm about to finish here, but I do want to focus a bit on the relativity of position. I think I'm going to do that in another video, a shorter one. But the relativity of position is just as dramatic in Galilean transformation as it is in Lorentz. And I want to focus on that because there's something I call the car and raindrop problem. And the question is, I have a rain cloud and a person standing under the rain cloud, and he sees a raindrop come down, or a raindrop form. Let's say he's got telescopic vision. He sees that raindrop form at x equals 0, t equals 1 minute ago. And a car is coming by. Doesn't matter what the car's current velocity is minus 1 minute. But at x equals 0, t equals 0, that car arrives here, and the raindrop hits the car, and at that moment, when the car is passing by and that raindrop hits the car is going 60 miles per hour. At that moment, the car assigns coordinates to the formation of this event, the formation of that raindrop. Where was that event? And this is a weird question, but this is the way you have to ask it. Where was that event now? Now, there's two parts of this question. I guess more than two parts. One, get it with the Galilean transformations. Two, get it with the Lorentz transformations. See what the difference is, if there's any measurable difference at all. And three, and this is the really important part of the question, do you have a problem with the answer? And if you do have a problem, can you describe the problem? And if you don't, because this is more of an opinion question, this is not a technical question, this is more of an opinion question. Do you have a problem with the answer that you got? If yes, can you get, because I'm assuming at this point you've gotten the correct answer here. If you haven't gotten the correct answer here, then this question is more or less is moot. It's not a good question, because if you get if you don't get the correct answer here, it's not your problem with the answer. It's just that you're not understanding you're not getting the math right. If the answer is no, then why do you have a problem with relativity of simultaneity? Because if do you have a problem with the answer? Yes. Can you describe the problem? Your problem is with relativity of position. You have a problem with relativity of position and relativity of simultaneity. If the answer is no, then you have no problem with you have no problem with relativity of position, but you do with relativity of simultaneity. And this is and I'd like if you have a problem with both, then I can empathize with you. I can feel that problem, that the problem with relativity of simultaneity and the problem with relativity of position are basically the same problem. And the problem is that you don't want to think that two objects occupying the same space at the same moment in time can have wildly different coordinates for the same event. Okay, so I will leave that question for another video, or if I get around to it. Thank you for watching.